Hello, my name is William Wilkes and this is a presentation on my project Kea Cavitometer. This project was sparked when my dad had an interesting time dealing with rather curious Kea in the Murchison Mountains. When he got home he shared all his stories and photographs.
This led me to ask lots of questions about Kea management. Keas are mountain parrots living in the South Island of New Zealand. I contacted the Department of Conservation Kea Management Team Leader Josh Kemp and discovered Kea were monitored as an indicator species for different types of predator control. Most of us have seen video footage of Kea soaring in the mountains or cheekily pulling your car to bits. This makes it easy to forget their vulnerability. They nest in cavities on the mountain forest floors, so the eggs and chicks are very vulnerable to predators. Accurate data on the nest outcomes is vital for evaluating how effective the different predator control regimes are. Keas have multiple nest cavities that they reuse, so not every site is in use every year. Access to the nest sites is difficult and expensive, and it is impractical for dock workers to monitor every possible site during the nesting season. Currently, dock use motion-triggered cameras to monitor activity around a nest site to determine whether it is in use. The camera is strapped to a tree 2 to 4 meters away from the track leading to the nest cavity. When a nest is in use, Kea will go in and out 4 to 6 times a day, and this results in 40 to 50 camera triggers. When the nest is not in use, there are 1 to 2 triggers per day. Some of the triggers are friendly, and others aren't. Monitoring this situation is both expensive and time-consuming.
I am working towards solving this problem by creating a device which dock can install outside each possible nest cavity. This device will then auto-report which nest cavities are in use over VHF radio, which dock routinely uses to monitor a range of species.
Because monitoring Kea like this has never been done before, first I developed a list of 6 risks and issues which would need to be solved in order to make the project viable. 1. Sensing the birds. Josh Kemp sent me a couple of broken cameras to help me reverse engineer some possible solutions. 2. Power supply. The device must be low power enough to ensure long life. 2 to 3 years is the minimum economic lifespan. 5 would be ideal. 3. Relaying the information. I had a number of options to relay the information. I worked through the pros and cons of each one to determine the best solution. 4. Sturdy hardware. The hardware must be able to withstand some extreme climatic conditions and investigation by intelligent and persistent parrots. 5. Small, lightweight hardware. The unit must be small and light, as deployment will be either manual or a combination of helicopter and manual. In both cases, mass and volume must be kept to a minimum. Cost. To be economic, each unit must retail for no more than $300. Sensing the birds. When I took the broken cameras apart, I found a piezoelectric sensor can. I did a lot of research and discovered the sensors work by detecting movement of patches of infrared radiation. Inside the sensors there are 2 halves, which are wired to cancel each other out. When the background infrared radiation levels received by each side of the sensor change, a fluctuation on the output is created. However, these fluctuations are microvolts and so very difficult to measure, especially due to the 0.8 volt offset created by the sensor. To make the sensor output useful, I have designed a processing circuit. The circuit is based around a quad op amp with a 2-stage amplifier and a pair of comparators. This gives a digital output. I used warm water bottles and chickens as Kea proxies to test the sensor.
The requirement for low power consumption under 100 microamps was a major constraint in my design. In order to make my circuit practical for use in this application, I needed to make 3 major adjustments. The op-amp was drawing 500 microamps, and this was a major problem. In order to solve this, I reviewed the options online and bought 3 likely contenders. I then measured their power consumption and chose the one with the lowest power consumption, which happened to be at 4.5 microamps. Secondly, I've modified the values of the circuit's reference resistors to give the right output voltages from the 3.6 volt rail I wanted to use. Lastly, I increased the values of the reference resistors, but kept the ratios the same. This lowers the current draw due to the higher values involved, but keeps the voltage the same due to keeping the ratios the same. This also created measurement nightmares because of the high impedances involved. To solve this problem, I had to make a high impedance buffer. I've chosen to use 160 MHz VHF radio for the auto reporting, as this is what wildlife transmitters use. This means I do not have to develop a unique radio circuit. I have asked Kea for permission to use their radio circuit, and they have agreed. After making these developments, I designed and manufactured my first PCB. While in the design process, I took into account things to make development easier, such as test points in relevant locations.
This was my first time soldering surface mount components, and I found it easy once I'd perfected my technique. Although they are not the smallest components available, they still must be handled with clean tweezers.
During testing of my PCB, I discovered an odd pulse on the output of the PIR amplifier. I investigated further and discovered this pulse was in sync with the radio output. When I looked into the problem further, I discovered that if I powered the board off a battery rather than an adjustable voltage regulator supply, the effect was exacerbated. I investigated this fault further and found thus some intermittent noise on the output of the PIR amplifier circuit. I traced this fault back to a faulty solder joint on one of the circuit's reference resistors. However, once I solved this, the pulse still occurred in sync with the radio output.
Next, I needed to set up the comparator referencers. However, this was difficult as my multimeter and oscilloscope both have 10 MΩ input impedance, and I was using them to measure the voltage across a 3 MΩ resistor. In order to measure the voltages accurately, I made a high impedance buffer from an old op-amp. This allowed me to successfully measure the voltages, and I set the limits at 75 mV above and below the output when it was stable.
Next, I needed to tackle the radio interference problem. I started by probing the radio and the raw PIR outputs. There was a fluctuation on the raw PIR output. Next, I tried the power supply. There was a fluctuation here too. I tried adding a whole myriad of smoothing capacitors to help smoothen the noise, but only a 10 nanofarad capacitor helped. This indicated to me it was a high frequency noise issue. I also tried using a low power regulator to isolate the supplies.
My bench power supply that I made based on a linear regulator damped the noise, so I thought adding a regulator might work. However, this too was unsuccessful. The solution which worked the best was to separate the supplies of the PIR circuit and run the radio and micro off two separate cells. This meant the current draw of the radio circuit could not cause the battery voltage to sag. This fluctuation affected the op-amps and the PIR, causing the pulse on the output. To try and damp the radio noise, I have swapped the tuning cap and one of the inductors out for smaller package sizes. This worked effectively, although I still have a small amount of electromagnetic coupling.
On the first prototype of my PCB, I solved the voltage sag and high frequency noise issues, but I have not been able to solve the electromagnetic coupling issues without major PCB changes. As you can see, I have completely redesigned the PCB to give as much clearance as possible between the circuits.
I made 4 major changes to my PCB. 1. I have powered the micro and radio circuit from a different battery to the PIR and op-amp circuit. 2. I have placed the batteries in the middle of the circuit board to shield electromagnetic noise and to create as much separation as possible. 3. I have used mainly SMD components to make the board more compact and reduce interference, while I have left the chips and comparator network resistors as through-hole for easier debugging. 4. I have used an on-board loop antenna rather than a whip antenna, which will allow me to waterproof the board more easily and make the units less vulnerable to curious Kea.
I've designed a manufacturing process to reduce the risk of errors and make the manufacture more efficient. This has mainly involved labelling components and storing them in accessible places. I've also resolved issues of lighting and ergonomics. I've already identified areas of improvement for the third PCB prototype. These include
circuit compaction. I can reduce the distances between the SMD. I can increase the size of holes for headers. I will use a manufacturer who can do plated through holes. This will mean I do not have to solder both the top and bottom sides of the board.
Currently, I have a rudimentary piece of software loaded onto the device for testing purposes. It is written in C for a blank 12F683 microcontroller. This is because Pickaxe does not have high enough timing accuracy at the low clock frequencies required to save power. I will need to write a full program for use in the field. I am working hard to finish 5 to 10 prototypes to be deployed in the field this breeding season. I still need to design the housing and write the software. The device will be tested in both hardware and software aspects. I will test it using proxy situations at home, such as chickens, to mimic Kea. Once the devices have passed through my proxy testing, they will be delivered to Josh Kemp, who will mount them on solid Kea nest cavities, which will also have cameras to test the effectiveness of my design. My aim is for the final cavitometers to be in place by next breeding season. Drop will require about 200 of them, so I'll need to carefully consider my manufacturing options. Thank you for watching this presentation.